Chapter 6, Section 2. We just talked about exponential functions, okay, with a base number that is a certain way and then an exponent that is the variable. So instead of the variable being at the bottom and then it having an exponent and doing things like parabolas and stuff like that, we're doing exponential problems where the base is a number and the exponent is the variable part. And so as we continue with that, it was discovered that there is a certain number that comes up in a certain placement, okay? Because we had A equals P times 1 plus R over N to the NT, okay? That's when we were doing compounded interest. And the R is the rate, and the N is how many times it is compounded. If it's once, then it's just 1 plus R, which is normal exponential function. But if it's compounded, like if it's done at monthly, you divide it by 12, or weekly, you divide it by 52, or daily, you divide it by 365. And it changes those numbers up a little bit. There's another number that's a special number, like pi and I, that came about because of this. Because as you continue to increase this number and that number, you get closer and closer and closer and closer and closer to a number, but never actually touch that number. Okay, you get this special asymptote. So if we look at this expression that goes with the natural base e, okay, natural base e is just a special type of exponential function where the base number is this e special number, like pi is 3.15, blah, 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 blah. Goes on forever, irrational. E is the same way. It's also an irrational number, does that. Here's where it comes from. 1 plus 1 over x to the x. So our time is once. Our rate is 1. But how many times we do it changes. The number of times we do it changes. Okay? So, as we increase the number of times, it gets closer and closer and closer to this line up here. You can see right up here that y equals e line. And our graph starts at 1 and then it keeps on going. It gets closer and closer and closer, but it never touches. You can see how the decimals change. 0.59, 0.70, 0.71, 0.71, 0.71, 0.71. And we get closer and closer and closer and closer to 0.71 something. Okay? That's where e comes from. It works just like any other base of an exponential function. So the same properties of exponents apply to it. So here's a definition of it. Here it is to certain decimal places, if you care to know that many. But the way that it works is the same as any other exponential function. If the base is the same and you're multiplying, you add the exponents. So e to the third times e to the sixth is e to the ninth, because 3 plus 6 is 9. When you divide, you subtract. Now we'd have to do the 16 and the 4. 16 divided by 4 is 4. E to the 5 over e to the 4, bases are the same. That's 5 minus 4. Okay, bigger numbers on top. So that's e to the first. Here, the same deal. Exponent goes to both pieces, both bases inside. We got a 3, we got an e. 3 squared, e to the negative 4x squared. 3 squared is 9. Negative 4 times 2 is e to the negative 8x. Okay, just like that. Here's some to try. Use those exponent properties. Give it a pause, give it a try, see what you get. Okay, e to the 7th times e to the 4th, add them together, e to the 11th. 24 divided by 8 is 3. 8 minus 5 is also 3. 10 to the 3rd is 1,000. Negative 3x to the third times 3, e to the negative 9x. Just like that. When we start looking at graphs of these, a function in the form of y equals a e to the rx is the parent function of the natural base form. When a is greater than 0 and r is greater than 0, so when a is a positive and r is a positive, it's a growth function. When a is greater than 0, positive, and r is less than 0, negative, it is decay. So you're looking at r. If this is positive, it's growth. This is negative. It's decay. The graphs of the basic functions y equals e to the x and y equals e to the negative x are shown. This is what their basic ones look like. Growth from left to right is getting bigger. The y starts out really close to 0 and then it gets big. Here it gets really big, starts really big, and then gets closer and closer and closer to 0. It decays, it gets smaller. Okay. Tell whether each function represents exponential growth or decay, then graph it. I really care about this part, the tell. We're going to use Desmos to graph. Okay. So this is positive. There's a 1 right there, which is positive. Positive, positive means growth. And if we look at the graph, y equals e, do the ABC button and then push e, it already knows, to the x. Goes like that. Oh, I forgot my 3. Hold on. Dook. Notice now it touches at 0, 3 instead of back here it touched at 0, 1. That's because we're plugging in 0 for x. E to the 0, anything to the 0 is 1. 1 times 3 is 3. So 0, 3 is where it graphs. Okay. And then let's look at this one. My a is a positive 1. My r is a negative 5 down. So it's going to be a decay graph. And then let's look. Y equals e to the negative 0.5 x. And it decays. Okay? And it decays. Starts up high, goes down low, off to the right. Ooh, hello. All right, here's a couple for you to try. I really care about this part. Tell me if it's growth or decay. Then I would graph it in Desmos and see if it matches what you think it is. Give it a try, give it a pause, come back. All right, let's look. A 1/2 is bigger than 0. A 1 is bigger than 0, so this one should be growth. 4 is bigger than 0, but this is less than 0, so that would be decay. Bigger. Bigger, both positive. That's going to be growth again. Okay. Now, let's look at the pictures of the graph and see if we can tell what's going on based on the pictures. Okay. We're going to have to deal with A and R here. What are they compared to 0? A, R, what's it compared to 0? A, R, what's it compared to 0? We haven't done a lot of graphing and talked about how A affects things, but A flips things over. If your A is negative, it's going to flip it vertically. So it's going to flip it from pointing up to pointing down. The R is going to flip it left to right. So instead of going left to right, getting bigger, going up, it's going to go left to right, getting smaller, going down. Decay. We're concerned about the R. Okay? That'll help us label it. But here, if we look at this one, we start above the x-axis, so A has to be greater than 0. And we're going from left to right, starting out small. This is really close to y equals 0. And then this is y equals 5. So we're getting bigger, left to right. So R is big, so this is growth. Now here, we're still above the x-axis. So that means A is greater than 0. It's a positive number. But this time we start up high. Here we're at y equals 5. And down here we're at y equals almost 0. Getting closer and closer but never touching. So that means we're less than that. That means we're decay. If I can spell it right. There we go. Now this time A is less than 0. Or A is negative. Right? Here A was positive. Now A is negative. But let's see what R is doing to figure out if it's growth or decay. Right? It starts out at, up here, at y is about 0, and then as we go left to right, you get y equals negative 5. Well, that is going down, so that is decay. So that means that my R is less than 0 as well. Here, my A is less than 0. It's negative. It's been flipped from up to down. And my R this time, I start out here at y equals negative 5, and I go up to y is approximately 0. That means we're getting bigger, so that's going to be growth. Okay? Just like that. Now, let's look at some of these pictures, or some of these problems from the book, because they get a little weird because the form changes. Remember that we're y equals a e to the rt. Okay? So our matchups, we've got y, we got a, we got a, we got t, we got t. So the 1 plus r represents our e to the r. Okay? So that's what we have to figure out. We have to figure out our r for that 1 plus r part, and it comes from the e to the r. So we're going to separate this off. Y equals e to the negative 0.75 to the t. So that means that e to the negative 0.75 has to equal 1 plus or minus r. Now in this case, I know that it's minus, and the reason I know it's minus is because my r is negative, which means I'm decay, and 1 minus r rate is a decay rate, so it has to be the minus. So if I want to know what r is, because what it asked me to do is rewrite the function in a y equals, so I'm going to fill in the blank, y equals a times 1 something, and I'm going to put in something for r to the t, and then I have to give it in percentage. R is a percent. So I'm going to move my r over, and so r plus e to the negative 0.75 equals 1. And then I'm going to move my e over. And so r is approximately, I'm going to have to round it, but let's see, 1 minus e to the negative 0.75. 5.28. 0.528. So I'm going to be minus 0.528. If I take 1 and subtract 0.528-ish, that's what I should get, the same as whenever I do e to the negative 0.75. Now that as a percentage, 52.8%. That's how they're looking for the answer. So let's look at 30. We got a y, we got an a, we got a 1, this time it's a plus r, and then we got a to the t. So down here in my answer, y equals 0.5 times 1 plus something to the t, and we need a percentage. We just have to figure out what r is. Well, e to the 0.8 should equal 1 plus r. This time I'm just going to subtract 1. E to 0.8 equals r. Sorry. Should be a minus 1 on there. Actually, we can just go ahead and round it, probably, is what we'll do. So let's do e to the 0.8 minus 1. 1.226. So r is 1.226. So 1.226. Let's rewrite that. 226 to t. So that's 122.6%. And that's what growth would be. If you're 100%, you're just you. To be growth, you'd have to be over 100%. You'd be 100 and a little bit more. If you're less than 100, like 52%, you've gotten smaller. You're not 100% of you. You're almost half of you. Okay? This one's 1 1/4 of you. That's what it should be. And let's look at, what is E? Excuse me. If I added 1 to that, it'd be 2.226. So what is E to the 0.08? 2.226. There we go. Comes out good. Now, real life problems in using E. One of the main reasons it is used, we looked at compound interest in the last, and it was A equals P times 1 plus R over N to the NT, where R was your rate, N is your number of times it's compounded, and T is for how long it's compounded. So if it was compounded yearly, it's once a year. If it's compounded monthly, it is 12. If it's compounded weekly, it's a 52. If it's compounded daily, it's a 365. But what if you compound it always? What if it's compounded continuously? Okay, that is a new equation. For compounded continuously, we use a equals p e to the rt, or a equals pert. Notice we've just done exactly what we did in our last problems, that 1 plus r is our e to the r part. Okay, so p is the principal, r is the rate, expressed as a decimal, and we get to use it. You and your friend each have accounts that earn annual interest compounded continuously. So we're going to use a equals p e to the rt. Okay. The balance A in dollars of your account after 2 years can be modeled by A equals 4,500 e to the 0.04 t. The graph shows the balance of your friend's account over time. Which account has a greater principal? Which account has a greater balance after 10 years? Well, the principal is your P. RP is 4,500. What was his? Where did he start? He started at 4,000. So who has the greatest principal? Okay. You have greatest principal. That's the first question. Second question, which one has a greater balance after 10 years? Well, what's his balance after 10 years? 4, 8, 12, 10. We go up to here. Let's see, 6, 7. He's a little over, I don't know, 7,250 maybe is what his is. Let's see what ours is after 10 years. So 4,500 e to the 0.04 times 10. Oop, oh, we want it up there. Time, no. I need parentheses. Times 10. Okay. Ours looks like 6713.21. That's how much we get after 10 years. And how much did he get after 10 years? Looks like he got about 72. See, I'm flipping back to my book here. I want to check. Make sure. Where is it? There we go. So if we say 7250, okay. So that, because the graph passes for your friend's principal is 4,000, the graph shows that the balance is 7. So your account has a greater principal, but your friend's account has a greater balance after 10 years. Okay? So what does that tell you? What does that tell you? Well, our average rate of change is bigger in his, so that means he had a better rate than we did to start with. Okay? So if we look at that, the friend after 10. Okay. Let's try it again. You deposit $442.50 in an account that earns 5% annual interest compounded continuously. So remember, it's A equals P e to the RT. Okay, so the amount equals $42.50 e to the 0.05. And compare the balance after 10 years with the accounts in example 3. Okay, example 3 was this guy here. So we want to know after 10 years. So what's the amount after we do 42.50 e to the 0.05 times 10? So let's figure that out. I'm just going to change my 50 and we're going to go 5. You get $7,007.07 after 10 years. So how's it compare? Well, it's better than yours, but still quite not as good as your friend's. Because you started out, it's supposed to be 0 in there. You started out with more than your friend did, but you still didn't gain as much as he did after 10 years. So his rate was better than 5% interest, which is pretty impressive. And so you'd write all that down. And that's the E. We're going to use it more when we get into logs in the next couple of sections, but You've got basic exponentials with a base number to an exponent, and